What's the name? Part of the you're doing. Okay.
Well, thank you so much for joining us today to celebrate Alex Brown's contribution to nuclear physics. And thank you for those who traveled from afar, Japan, and thank you to those who join us on Zoom. Japan, Spain, Austria, Israel. Maybe that's it. Thank you for staying up late or getting up early. But we're here to celebrate Alex's contribution. There's few who are as prolific and as impactful in their contributions to physics. So Alex, thank you for what you've done for MSU, the lab, the community, and for working with experimenters, interpreting data that can be measured. And maybe that's due to your origin as an experimenter. So, you know, an experimental physicist, appreciate your contribution also. And I think that's all I have to say. I appreciate you all coming. Look forward to the program. Thank you.
Okay, thank you very much. Welcome also from me for coming here. So I will be chairing the first session, but in the beginning, I would like to remind you that we are following the FRIB code of conduct. So we strive to create a welcoming environment where everybody feels safe to speak up, and we will not tolerate harassment. And we, for the meeting, we put ourselves in particular under the Code of Conduct for the FRIB Theory Alliance, which we have printed out next to the food outside in case you want to look into details. And with this, I'm very happy to call on Alfredo Porres from the University of Madrid for the first presentation. Alfredo, it's all
Thank you, Alex. I'm sharing my screen now. I hope it works.
Yes. Yes.
Well, thank you very much for counting on me for this very special celebration. I'm sorry not to be with you there in person, but I will follow all the day here in my computer. So my title is The Nuclear Cell Model, a long and winding road that you remember if you're old enough. Where this comes from, I will not say it. And the outline will be shown little by little. So let me start with a few personal notes. I met Alex in 75. So it's 75 first time at the Varena Summer School. And at this moment, it was a great moment of Copenhagen, and not many cell model practitioners were there. Wildenthal told me only among the professors. This was a 2 weeks school. And at this moment, I was really starting, just at the middle of my PhD. Some of you will remember that the same year, 75, there was this called Tucson crisis about the how to do the things properly, what we should call, we call now ab initio, but this crisis made many people, or some people, to lose the hope of linking the bare nuclear interaction and the spectroscopy of complex nuclei. At the same time, the experimental physics, which was fashionable in this period, was the high-spin physics, and there we, the cell modelists, were at this moment in clear disadvantage. So the interactive boson approximation and the mean field, Strutinsky, etc., description took the lead. And only like in aesthetics, a few irreducible cell modelists persisted, and I have listed there a few names. But again, in 75, Catherine Thibault measured the mass of sodium-31, And this was incompatible with the semi-magic nature of the n equal the number of neutrons being 20. In a sense, the field of nuclear far from stability of exotic nuclei, that FRIB is now the rising star, was born. It took more than 10 years to understand the phenomenon of the island of inversion, and nowadays is one of our favorite places to work. Alex and I have shared many physics themes for many years. And as Charles the Emperor told to François Premier, the King of France, they both like Italy, with both like the n equal 20 island of inversion. To explain this behavior, it was necessary to have two major shells in the cell model context, and realize that the real actor there were the quadruple correlations. Warburton, Becker, and Brown coined the term island of inversion, and my latest student, Rita Mosna, and myself would have preferred to dub it island of deformation. And if you look to the two papers that were pioneers, in the title, there is the word deformation, both the deform A equal 32 and the onset of the deformation. So there was good reason for that. Okay. I assume you all know which are the pillars of the shell model. You need to define a valence space, an effective interaction, and shell model codes or approximations. And I will really touch very rapidly these things. In '88, Alex and Wildenton, in his review, wanted that in the future dimension be increased 1 order of magnitude to about 10 to the 6, 1 million in M scheme. The situation moved very rapidly first with the Antoine shell model code of my friend and collaborator Etienne Corrier. I think he did at the very moment he gained 2 orders of magnitude instead of 1. And nowadays, calculation of the dimensions 10 to the 10 are routine, and new codes and approximation can deal with that. The effective interactions is a crucial point, as you all know, and until the renaissance of the ab initio program, some 10 or 15 years ago, there were 3 main paths to obtain the effective interaction. One was just to fit the 2-body matrix elements to a set of experimental data, or in the other extreme, the ab initio 2-body matrix elements. So you started with the nuclear interaction that reproduce the deuterium data and the phase shifts, renormalize it for get a G matrix, you renormalize it for a given valence space, and that's it. Well, as I will maybe comment, this ab initio program was seen to be a very limited applicability, and when you had many particles in the valence space, there was an intermediate route, which was the monopole corrected ab initio 2-body matrix elements. This was proposed by Andres Kruger. In principle, this idea that the only wrong thing in the ab initio 2-body matrix elements, the only problems were with the monopole part, it has become accepted after many years, and nowadays the 3-body interactions of the new wave of ab initio calculation seems to cure some, if not all, the monopole anomalies. Good luck to the new ab initio. But I wanted to present a funny historical reconstruction, which was just, I am used to take the original Kuo-Brown interaction, 78, and do the full PF shell calculation with this interaction. And the first thing that I did is chromium 48. And if you look rapidly to the table, you can realize that Kuo-Brown was essentially perfect in describing the spectroscopy of chromium 48, which is a well-deformed nucleus in the PF shell. Look to the B of E2s, to the ratios, etc., etc. So at this, if you had the computer, if they had the computer and the code to do the calculation, they could have described, give a superb spherical cell model description of the IRAS band of a well-deformed nucleus. And somehow the ab initio description of nuclear collectivity dates more than 50 years back in time. And that is, I forget, one of the masters, one of the real masters of our field, which is Phil Elliott, that had that in a very more limited context, but many years before. What happened if you do the same with the Kuo-Brown interaction and you compute nickel 56? But this is very funny. Nickel 56 with the Kuo-Brown interaction is a perfect super deformed oblate rotor with beta equal 0.43, and the ratios of the energies of the 4 to the 2, 3.2. The double magic configuration disappeared completely, and the ground state band is of 8 particle, 8 hole nature. Look to the numbers, the 2 plus at 0.5, a huge, well, everything. This was in complete contrast with the experiment, contrary to the case of chromium 48. So Kuo-Brown was very good for the deformed. Kuo-Brown interaction wanted to deform everybody, including the double magic. In addition, I hope you're listening to me.
Oh, yeah.
Are you listening to me?
Yes.
Okay. In addition, Kuo-Brown does not produce a double magic calcium 48. Does an excellent job for calcium 52 and makes calcium 54 the strongest double magic nuclei ever. The 2 plus is at about 5 MeV or something like that. Really, really, really a spike in the 2 pluses. That's what Kuo-Brown does. Obviously, we are counterfactual. But the fact that when you add many particles to the valence space, the result deteriorated was in a sense a bit part of the crisis. And then the purely phenomenological approach, let's say, do a fit to the two matrix elements, took the lead of the cell model calculation for many years here. Wildenthal and Alice were the masters of the game, and the universalist interaction has been one of the key important milestones of nuclear theory, I would say. Well, it is easy to say things with hindsight, but now we can do that. All the problem with the Kuo-Brown interaction was that the gap in calcium at n equal 28 and the gap in nickel 56 at n and c equal 28 was very, very small. And this, it couldn't compete with this gap, the many particle, many hole excitation that were gaining energy because of the quadruple correlations, etc., couldn't couldn't be resisted by the spherical mean field. That's why nickel 56 was such an incredible rotor. So just changing one monopole, restore the gaps, was enough to produce everything in the PF shell essentially. And in addition, and I'll go to the next slide, which is has a message, using this diffuse Zucker construction, which is just to find which are the coherent multiple parts of the effective interaction. It is seen that at first order, the multiple part of all the effective interaction, be it fitted or G matrices or whatnot, is universal. As I cannot enter in many details, and as you will have many ab initio stuff, in this table I have put this coupling constant, coherent strength of the effective interaction. But just go to what is NN and NN plus NN. And this is the content of the interaction that the present in the lecture room people like Bogner and collaborator made in 2014 with the medium similarity renormalization group. And these matrix elements, you take out the monopole and you take the two-body part, you see, yes, not to confuse you a lot, that the standard isolector pairing has a coupling constant of 4.38. In the lowest row, you do the same with the two-body and three-body part, and the coupling constant is 4.36. And if you go, not to confuse everybody, to the another big chunk of the nuclear-nuclear interaction, if you go to the quadrupole, you move from 3.35 to 3.28. So it doesn't move at all. In view of this result, and considering that the monopole-corrected two-body ab initio interaction, already many years ago, Andrés Zucker surmised that everything could be solved with a monopole three-body. And that I can put it a bit further for the benefit of my friends and colleagues, that the surmise now is that the main effect of the three-body is its contribution to the monopole Hamiltonian to provide the right evolution of the spherical mean field in the valence space. And there is some recent work of the Napoli group that goes in this direction. In my opinion, this could simplify enormously the valence space in medium similarity renormalization group calculation. But at the end of the day, the dimensionality barrier will apply to every approach. So there are always things to do in this context. I don't know, Alex, I have 2 minutes?
Yes.
Yes?
Yes, 2 minutes.
2 minutes, yes. I cannot close that without mentioning Elliott, as you all know, that solved the problem of the quadrupole interaction in one major oscillator shell in 58. And this was really one of the brilliant moments. And I think this idea of the quadrupole dominance must be behind all our tables. But the important thing is the limitation of SU3 as an exact symmetry were extended later to other valence space, creating variants of SU3. You know well pseudo SU3 that applies when the valence space is an harmonic oscillator excluding the intruder orbit, or quasi SU3, in which the space comprise the intruder orbit and its quadruple partners. In all these circumstances, the quadruple correlation will thrive. And this has to do with all the problems of island of inversion, shape coexistence, and all the most of the funny things that we encounter in nuclear physics. And clearly, this is the case for the island of inversion. It is now common knowledge, I would say, that the island of inversion occur when the neutron magic gaps in the very neutron-rich isotope are quenched somehow, but only provided that the intruder configuration can maximize their correlation energy, which is mainly of quadruple type. For that to happen, the orbit close to the Fermi level must pertain to some of the SU3 variants. For instance, at our dear n equal 20 island of inversion, the proton orbits form a quasi-SU3 sequence. The neutron holes are in pseudo-SU3, and the neutron particles again in quasi-SU3. So if you make a many particle, many holes, this will maximize and maximize the quadruple correlation energy. This together with the fact that going to oxygen 28, the SD-PF gap is getting reduced, well, just produce what our friends will call a quantum phase transition from a spherical to a deformed regime. It is more or less the same at n equal 40 and all at n equal 50 and all around. And also it is also the mechanism driving the formation everywhere. For instance, in zirconium 80, you have the same situation. You have all these situations all around when the intruders become dominant and then the formation sits in. Okay, that's the end of my messages. You have realized that I have put only one formula, which is the formula of Elliott, and so I finish here. Congratulations, Alex. It's a pleasure. I hope it will be. We will continue working, well, interacting and collaborating. You had a really impressive career, and this is my last 25, which is Varena 25, where you can see in the first row Alex in 1925. Thank you very much for your attention. And again, congratulations, Alex.
Thank you very much for this nice walk along the long and winding road. We have some minutes for comments or questions while I'm changing talks for the next speaker. Maybe unshare.
My only comment is that that was in 76. That was
Oh, Alfredo had a mass error.
I think it was 70. Huh?
Was 76. So clearly I was trying it to be in 75 because of 75. Huh?
Yes.
Obviously, you are entitled to change the dates if you have a good goal.
Yes, we approve.
Thank you.
Thank you very much, Alfredo.
I will then stop sharing.
Yes, thank you very much. And the next speaker traveled from very far, and it's Taka Otsuka from the University of Tokyo and Riken. And once I find his talk,
Here it is.
there it is. Remind us of milestones and prospects. I cannot download from your Google Drive.
But then it comes.
Okay, so please take it away, Taka.
Yes, could you raise up pointer on this microphone?
Pointer options.
Yeah.
Laser pointer, there you go.
Thank you. Microphone. I don't think he has a microphone now.
We are not using microphones in the room because they're picking it up.
Oh,
Okay, if you could just speak a little bit louder.
okay. So, good morning,
Oh, but you should wear that if you move around. Because
okay.
the camera will follow you.
Yes. So, good morning, everyone. I'm very pleased to be here to celebrate Alex's 75th birthday. This is exactly today, is that right?
Yeah, I think so.
Yes. And I'm very honored to present this talk today about the milestone and prospect of the shell model. Let me start with some personal touch. So Alex came to Tokyo as the So Alex came to Tokyo as a prestigious JSPS postdoc fellow. After his time in Stonewall, he joined the group of Professor Akito Arim. I saw him in 1974, I think in April, when I joined the same group as graduate student. So Alex is probably 4 years old, 4 years older than me. I did not know what he was doing with Akito because I just joined. But Alex gave a major impact to everyday activities because of Alex and also due to some other foreigners in the department, official language was suddenly switched to English. So it's quite an experience to me and also to some other students. At that time, Professor Jean Sprouse was visiting Professor Yamazaki. And then Mrs. Sprouse taught us how to talk in English. It was very helpful. I have many nice memories with Alex at that time. We used to have dinner in a nearby restaurant, which is called the Morikawa-cho Shokudo. Yeah, this one. And it was really every day during the week. And we go there, 5, 6 people. And Alex managed to order in Japanese. It was quite amazing. But it's basically the same thing, lunch, salad, right? Also, it was dinner, but since Japanese do not know English so well, then it is a lunch. The menu is lunch, but for dinner. But the lunch was changing every day, so he couldn't get bored. And you know Kuniharu Kubodera from North Carolina, I think. He was the research associate at that time, and he was often with us. Well, Akito started the interacting boson model at that year with Franco Yakero. He went to Groningen and he came back, I think in September or so, and gave a seminar. Alex raised a question after the seminar. The question was, what is the microscopic foundation? Well, now I understand this is quite a natural question, but at that time I was very young. Then I was quite impressed by such a fantastic question. But of course, I did not know that I would struggle with this question for decades. Yeah, it was quite interesting memory. Well, now let me move on to the shell model. So in 1949, officially, Gebhardt-Meyer and Hans Jensen, Maria Gebhardt-Meyer and Hans Jensen proposed the shell model. There are maybe two different theories about the beginning of the shell model. One is 1948, the other is 49. But in 1999, they organized this conference in Heidelberg, 50 years nuclear shell model. So the organizers defined the shell model was started in 1949. So next year is actually 75th anniversary of shell model, but since Maria Gebhardt-Meyer published the first paper in 1948, this year can be also 75th anniversary. And the model they proposed is actually independent particle model. And also the pairing correlation was included to extract the single particle properties, but in it is independent particle model. Later, the shell model became many body approaches with the correlations by nuclear forces. One of the earliest example is the configuration mixing by Lima and Fourier. Yeah. In my opinion, one of the major milestones of the shell model was placed by Alex by introducing several sets of realistic effective interactions, which Alfred already mentioned, and also by making codes for the diagonalization with full major shell configuration accessible for everyone. I think this is a very important point he made. The actual interactions WBP, WBT, USD, up to USD, USDA, USDB. Then more recently, JJ44, JJ55, I don't know how many, like JJ100, 100 or so. But anyway, he produced many useful realistic interactions. And all those interactions are sort of fitted interaction, but the idea is to combine microscopic calculations and fit. So it's not completely fitted interaction, but also mentioned by Alfred. And the shell model codes are Box-Bash and the new shell and so on. But the important thing by Alex is he made all those calculations accessible to everyone, not only theoreticians, experimentalists, and students. So I think then the shell model became very useful tool for general nuclear structure study. Important, but also Alex made a proper assessment of the interaction, so people can use those interactions without worrying about their validity or limits and so on. That was very important, I think. Then, I know that Alfred will mention island inversion, so I'd like to mention another important physical milestone by Alex. That is this thing. So this is the paper by Alex, published in 1993 in unknown Mexican journal. And this is the binding energy of oxygen isotopes. And here points are experimental data, and they are shifted to different theoretical calculations. And if you look at this part or that part, those are calculations with two realistic shell model interactions. And indeed, those interactions produce drip line of oxygen at oxygen 24. And he compared those results with the result by Melanic's global protection. Then in this calculation, oxygen 28 is still bound. So this is a very important achievement by Alex. And also this is an extension of Tarumy's argument that interactions between identical nucleons are repulsive in average. You have to be careful about this in average because but anyway, so it was very important extension. And this importance can be seen by looking at the effective single particle energies of oxygen isotopes. So this is what Alex showed in that paper. then D5 halves, D3 halves get apart like this, to the repulsive effect. And later, much later, like in 2010, we made some calculation by applying Uchida-Miyazawa delta Hall excitation, and then it produces three-body forces, and we can obtain effective two-body interaction from that three-body force. Then we get basically the same thing. So Alex did it well before such microscopic work. So those are quite amazing. And of course, this three-body forces are still studied by ab initio calculation. That was quite important. And then we worked rather closely at the beginning of this century, and we have those papers together. This paper that is about the variation of N equals 16 gap. I mean, N equals 16 gap exists in oxygen, but not magnesium and so on. So we worked on this issue from shell model calculation, and also we predicted N equals 34 gap may appear in exotic calcium isotopes. Another work we did together is the derivation of GXP interaction. Alfred also mentioned this, and this is basically continuation of USD interaction from SD shell to PO shell, and Homer did a calculation in collaboration with Alex. And yeah, that is exactly the application of the basic idea of USD to PO shell. But it was very much enjoyable days of shell model calculation. We can try to fit many experimental data by playing two-body matrix element a little bit. Then we can say, oh, now we can use this data and so on. And this interaction is still useful. And also, this became the mother of more advanced interaction. So, so we had a very nice collaboration around that time. Now, this conference must be also on the future of nuclear structure theory. So let me move on to this subject. And then I'd like to take these two things, find deformed shapes, just as alpha clustering. Yeah. About okay. Let me start with this picture. Okay, this is a 2+ energy systematics observed. The upper figure shows 2+ energies of stable and long-lived nuclei. Then you can see many spikes, and those spikes correspond to magic numbers, which Meyer-Jensen predicted. But if you plot all measured 2+ levels up to 2022, then more peaks are there, like oxygen 24, calcium 52, calcium 54. And those new magic numbers and also other cell evolution phenomena are driven partly by the tensor force. And that is a new aspect of cell model calculation. And but if you look at the heavier regions, you don't see such peaks. So its tensor force disappears in deformed nuclei. That's not true, because in those deformed nuclei, the nuclear structure is governed not by shell structure, but by deformation. Then it is interesting to see how the 2+ and 4+ state behaved in those regions. Then I made this plot based on new data 3 database, and I picked up 2+ state with 4+ 2+ energy ratio greater than 3. All the levels from proton up to 8. I was surprised. If you look at this region, that is the mass number below 80, only 5 nuclei satisfy this condition. Magnesium 24, sulfur 42 and 3 exotic magnesium nuclei. This is we understand, but sulfur 42 is quite interesting because also if you calculate potential energy surface, it's almost perfect flow rate. Magnesium 24 may deviate a little bit. So even calcium sulfur 42 could be one of the best example of SU3 nucleus. On the other hand, those exotic ones are very different. They are quite triaxial, but they show strong deformation. So this shows that maybe the exoticity in nuclei are very important for strong deformation. And that is true also in this region. Here, just 5 nuclei from strontium, zirconium, Mori region.
Excuse me, can I say something?
No, we let Tucker finish his talk.
We do not, the Zoom people don't see the slides.
Yes.
Yeah, slides are not changing.
Ah, okay.
Just technical problem.
Is it changing now, Naftali?
Yes, now we see.
Yes, now we can see it. Thank you.
But at the end of the talk almost. Okay.
I tried. I said hide it.
Fine. So,
Hide floating panel. Hide floating, yeah, that front there.
Okay, good. Okay, then from those 5 nuclei show also strongly deformed cases, but many of them are actually exotic ones, like zirconium 100. So the exoticity with neutrons is quite important for large deformation. However, the story becomes very different if you go beyond 140. Now we have many nuclei showing strong deformation. I mean, this ratio greater than 3. And there are actually 66 nuclei showing this ratio. And as you know, the Ajeboa described this kind of nuclei with prorate deformed shape for ground band and gamma vibration for the sideband like this. And this explanation survived more than half century. The preponderance of prorate shape is one of the common sense of nuclear structure physics. And other theories support this picture. For instance, from this Peter Miller and his collaborators studies, if you look at this region, all nuclei show axial symmetry. And now the shell model can handle this kind of situation with its Monte Carlo version. And recently we developed within Monte Carlo shell model to KSI particle vacuum shell model. Then we can really describe structure of those heavy deformed nuclei. So I'd like to show you an example now. And this is a result. And if you compare Ajeboa's picture and our picture, there's this difference. With Ajeboa, this state is this kind of gamma vibration, while the ground band is made by rotating this object, which is actually symmetric here. But the new shell model result indicates that the ground state is not actually symmetric, but it's ellipse in this cross section. So it can rotate this way, like this, but also it can rotate this way. And this 2 plus is a result of this rotation. And then by this wave function, we can reproduce many experimental data. So Then we have two different pictures of the same type of states. But in this approach, the tensor force is shown to be essential for producing triaxial shapes in heavy deformed nuclei. Now I'd like to show you how actual deformed nuclei show the shapes. So those colored points indicate strong deformation, and this part is triaxial. Triaxiality means second 2 plus is below second 0 plus, and this is another group, also triaxiality. So from this figure, you can already see that the triaxiality may be the key aspect of really many heavy nuclei that is not the same as what Ajibova projected. Now, let me move on to the clustering, just 2-3 minutes. Yes,
2 minutes,
okay.
1.5.
Okay. This is another new result from recent shell model calculation, and this is a completely different approach. That is ab initio no-core Monte Carlo shell model. This ab initio no-core shell model has been done by many people, and I think Peter Navratilova will talk about that. Then, but then we combine this promising approach with the Monte Carlo shell model, and taking many shells, like 7 harmonic persistent shells, using the zone 16 interaction, which was obtained by EFT, chiral EFT. Then this is the result. So there's no fit, but 2 plus energy comes out right, and also B2 comes out right with those free charges. But what another interesting feature is the alpha clustering in the ground state and Hoyle state. This is the density profile, ground state and Hoyle state. So even ground state contained 6% of clustering component in it, and the Hoyle state is not completely clustering. It contains 33% of quantum liquid component. So this is quite interesting because usually the clustering was associated with loose binding, because once the nucleus gets loose binding near alpha threshold, then alpha can be formed. That is a traditional understanding, but we can see that nuclear forces, which includes up to short range part, actually mix normal nuclear matter and clustering component, and this is shown for carbon 12, but same thing could happen in heavy nuclei, and this might hint the alpha clustering formation in heavy nuclei, which must be related to the alpha decays and so on. So I think this is the last slide. So we know that the UNIDEF website shows a very nice figure, but I a little bit added this part. So maybe CI configuration interaction can handle this part up to yesterday, but now we are moving to this region, and actually this region is the region to most advanced RIB facilities like FRIB or RIB. They are aiming at new experiments in that region, but our theoretical efforts are also coming to the same region, so we are in a completely same phase for new physics. So that is very nice timing. And Alex promoted the shell model movement. This is actually really good movement. I mean, people encouraged to see, to do shell model calculation, to see shell model result. I think his contribution is enormous in this aspect. Without his effort, shell model could have remained more technical or professional. And luckily, the shell model, including global activities, as Alfred already mentioned, seems to have gone unexpectedly well with some new findings. So I'd like to thank Alex for his enormous, important, valuable effort. And I brought this one to him. Many Japanese are thankful, but they cannot come. But they contributed their message And I'd like to now present to Alex. Thank you very much.
Thank you very much for this fantastic presentation. We have some time for comments or quick questions. I'm figuring out, Sophia made it, where the next speaker is. That's your chance. Yes, please.
Could you go back to the graph with the there's X and Y and then there's a Z axis? What was on the, yeah, that one. Yeah, that one. What was the vertical axis?
What is the Z-axis?
The axis is the density.
Okay, thank you.
Intrinsic frame, yes. So this is alpha particle density distribution. This is ground state density distribution, and this is density distribution for the coil state. And those are decomposition of them.
We call this was done with Dejon 16. You said
Yes, it is.
Was any other interaction tried at all?
No, because the calculation was very expensive. We can use just one interaction.
Sounds good.
Maybe in 5 years we can try other.
Okay, I think we should move on and thank
Okay.
Taka again. We can continue discussions if we ever have a coffee break, because I'm about the worst chair you can have. It's my pleasure to now call on Sophia Kampaya, who used to be a postdoc with Alex and Vladimir from Grand Valley State, so she could drive in this morning. Really the worst chair. Which one? It was the wrong USB one? Yeah, I think it's Samsung.
Then we go to past future year somewhere. And now we go to this one.
You have a lot of talk.
Thank you.
See.
Okay, can people see the slides changing? Okay.
Yeah.
Wait, Sophia.
Hello, everyone. Today I wanted to talk about how the nuclear cell model has managed to breed nuclear structure studies with nuclear astrophysics. And it's quite amazing, actually, because we know that the cell model, we use the cell model for nuclear structure, but how can we take nuclear structure information and integrate it for nuclear astrophysics studies, since we know that these are studies that range in an extensive, in a huge energy range, and for multiple, and for many isotopes. So this was actually made possible as the previous owner, as the previous speaker talked with the development of the effective cell model and the phenomenological effective cell model Hamiltonians. So starting from 75 years ago, everything started with the extreme single particle model, where each nuclear level is described by a single nucleon occupying just a single particle energy. And then we moved on to each energy level being described by a configuration of multiple protons and neutrons. And this was made possible mainly through the development of phenomenological effective cell model Hamiltonians. Now, a phenomenological effective cell model Hamiltonian is when you take single particle energies and the two-body matrix elements, and you fit them using experimental data. You have a core, the lower energy orbitals where the nucleons cannot be excited from the core, and the valence space, which is partially filled, and the nucleons can move around the valence space and occupy different orbitals. Then we have higher cells which are empty, and of course to describe the effects of the excluded configurations, because nucleons cannot move around in other than the valence cell. Some is necessary. So these efforts started from small cells like the F7 half cell back in the 70s and 80s, and moved on up to PF cell and really neutron-rich nuclei close to the PF cell. With these interactions, and these are interactions that have been developed by Alex Brown and collaborators. And these interactions have really pushed towards us talking today for applications of the nuclear cell model towards nuclear astrophysics. And of course, today and for the future, we are starting to see interactions that have the nuclear cell model being solved using ab initio methods, or the nuclear cell model in the framework of no core, using no core. These are the nuclear reaction processes which are responsible for the synthesis of elements in the universe. And let's concentrate on the R process, which is responsible for the production of more than half the elements heavier than iron, which proceeds via successive neutron captures and beta declares. Now, the simulations, so for the R process, we use simulations which require various nuclear physics inputs, such as masses, half-lives, fission rates and yields, and neutron capture rates. Now, for masses and half-lives, we have extended density functional theory calculations. But the nuclear cell model has also provided half-lives up to about mid-sized nuclei. Now, for neutron capture rates, wherever there are no available experimental data, calculations are performed within the statistical Hauser-Feshbach approach. And the main ingredients within this approach are nuclear ion densities, gamma ray strength function, and the optical model potential. Of course, you cannot use the Hauser-Feshbach approach when the neutron capture reactions have low P values. This is a slide that shows the impact that different nuclear level density models and gamma strength for gamma ray strength functions have on neutron capture rates. So these are different models within the reaction network, reaction called TILES. And these are the ratios of neutron capture rates, the highest to lowest ratios of neutron capture rates using these different models. And you can see that even for isotopes that are just 2 neutrons away from stability, these ratios can be as large as 20. And so there is this need for reliable theoretical calculations for nuclear level densities and gamma functions. Recently, in 2005, they found experimental evidence of a low energy append in the gamma ray strength function. The gamma ray strength function is a measure of the probability of nucleus emitting or absorbing photons. Now, the gamma ray strength functions has various resonances which have to do with the collective motion of protons and neutrons. Now, all nuclei have this dipole resonance, which is of E1 character, and it's when protons and neutrons move against each other, and the dipole resonance when excess neutrons move against the proton-neutron coefficient. For deformed nuclei, the scissors mode becomes important, where protons and neutrons again move against each other, but in a scissors-like mode. Now, the low energy part of the gamma ray strength function was supposed to be described by the low energy tail of the gamma ray strength of the giant dipole resonance. And they used this generalized Lorentzian functions to describe the giant dipole resonance, but these functions cannot describe this low energy append, and these are all the nuclei that have been studied experimentally for a low energy append. With yellow, it's all those nuclei that where they have found this enhancement of the gamma ray strength function in the low energy. Red is where they have not found it, and blue is where they were not sure whether experimentally there was such an enhancement. And this is the impact that this low energy enhancement potentially has on N gamma reaction rates. So what you see here is the ratios of neutron reaction rates for multiple isotopes at temperatures 10 to the 9 Kelvin, here for a smaller temperature. These are the ratios of the neutron reaction rates, including the append and without including the append, using different models to describe the append. And you can see that the append becomes increasingly important for those reaction rates as the number of neutrons increases. Alex was one of the first to perform cell model calculations using this effective interaction, the GX-PF1A, and showed that this low energy append in the gamma ray strength function for iron 56 and 57 is of M1 character. He also proposed in this work with Cecile Larsen that the main contribution to the append is through transitions within orbitals of high J value. And this study was the function was worked on more with in this study where we picked only the F7 half cell to see whether we can observe the append in the low energy part of the gamma ray strength function. Then Alex moved on and found that the low energy append and the M1 scissors mode are connected. So in this work, they used multiple iron isotopes And toward itself, the iron isotopes, the scissors mode becomes important. And this removes strength from the low energy, from the M1 contribution of the low energy atom. Now, in the study of level densities, now there are, we have experimental information on the low energy, on the nuclear level density from multiple experimental data. First from low energy discrete experimental levels, and then we have level density from resonance spacings at the neutron separation energy. Recently, the Oslo method and the beta Oslo technique have been providing nuclear level densities in the in-between regions. There are also the other techniques like the particle evaporation from compound nuclear reactions that also provides nuclear level densities. Phenomenologically, so the nuclear level density studies use mostly our models to derive level densities. So we have phenomenological models like the Fermi gas and the constant temperature model that are widely used. And then there are macroscopic models like the Hartree-Fock calculations, which have provided nuclear level densities for multiple isotopes and extended energy relevant for astrophysical applications. Then when we go to cell model, the cell model Monte Carlo is one of the ways to derive nuclear level densities within the cell model for mid-mass and heavy nuclei. And recently, the moments method, which is also based on cell model, has been it's been used to derive nuclear level density. But Alex, together with Ormond, used the Lanxess algorithm within the nuclear cell model to derive information about nuclear level density. So they were able to compute the first 8 moments of the Hamiltonian using the Lanxess algorithm. And here is an example from this study where they have derived the nuclear densities for positive, negative parities. This is an example on the germanium-74. And the comparison of these nuclear level densities with experimental data from the Oslo method and the particle evaporation method used in Ohio State. Of course, there are many more nuclear physics inputs which are significant for nuclear synthesis studies and which Alex has contributed vastly. There are gamma-Taylor strength distributions studies for electron capture and beta decays, and studies which show how these affect the impact they have in astrophysics, spectroscopic factor calculations, and information on excitation energies of nuclei involved on the nuclear reaction. Thank you.
Thank you very much for this nice presentation and for reminding us of the importance for the shell model for astrophysics. We have time for a few comments or a brief question. You can also snatch her during the non-existing coffee break or lunch break. Well, I'll let you do this. Okay, then thanks again. Okay, it's my pleasure to welcome Mihai Horoy from Central Michigan University. PDF, correct?
Yeah, is that good?
We take anything. Hit the downloads. Hit the download.
Scanning.
Oh, scanning for viruses. We are very safe here. Yeah, I realize that.
Make it full screen.
This place in the browser, so that's no.
You click the three dots. The three dots.
I want to open it in new window.
The horizontal three dots. Yeah. Yes.
With Acrobat, there you go. This is what I said.
I can do it from my iPhone.
Hey. Okay.
Okay, thank you. Sorry for the extra time for that, and thank you, the organizer, for inviting me. And, start my talk. Certainly we're here to celebrate Alex's 75th birthday, and if I counted correctly, it's about 50 years of nuclear physics. There's no dispute with Alfredo. Yes. Incidentally, it's also almost to the day 30 years since I arrived here. It was October 2nd, 1993, and Alex graciously waited for me at the airport with a late flight from Chicago. So we barely slept about 4 hours, and after that we moved to chair lane, which does not exist anymore. Now it's a chair lane path. But it happened that we changed some email, and I was trying to use Oxmarch code, and actually we were Humboldt fellow in about the same time. I was in Gießen, and Alex was a senior Humboldt fellow in Darmstadt. It was 92 to 93, and I visited him in Darmstadt, and also he visited me in Gießen, and after that I came here. And at that time, I actually was doing some research on parity and on conservation in nuclei, relatively complex nuclei. And that's a couple of papers, so we can see this 93. And after that, I came here, and we can see actually in 94, I published something else. Actually, so it's a new experiment. They're both new experimental proposals, which are never done for various reasons. But regardless, that was what I was doing at the time. And
same time I was actually working with Alex on this carbon 13 plus P and nitrogen 14 nitrogen conservation, which is also a reaction. And the experiment was done actually about the same time in Seattle. And we calculated, it was a heavy calculation, Ernie Warburton, the late Ernie Warburton was involved in this. And we used the shell model, which have several energy bar omega included here, and we showed that in fact, if you take only the zero energy bar omega, you might be wrong, because the transition involved with 2, 3 energy bar omega actually may cancel out, and that solves some of the problems. And in the end, it solved the problem, the general magnitude of the observable, but it didn't change the sign. So the sign was wrong, and I believe it's still wrong today, but I didn't follow all the developments. So after that, we actually published a review paper in which we put all the experiments and with new calculation, and this was showing at the end that we have 2 couplings here. They tend to be consistent if you analyze some of the experiments which were available at the time. Okay. So again, at that time, I believe Alfredo mentioned that we have there was this issues with the shell model, and in particular, there was this NH bar omega catastrophe, and we still were able to do some down-to-earth calculation and gain some insight into the problem. So I believe this was kind of my last contribution to the paradigm of conservation, which is still a interesting subject. And because I came here, I started collaborating with Alex and Vladimir, and we moved on to do some investigation of the properties of the shell model, eigenstate and eigenfunction. And we published a paper regarding this chaotic properties of the eigenvalues, shell model eigenvalues, and look to properties of the components of the wave functions. Investigated the temperature in nuclei, which is another interesting subject. And that actually was quite useful in the end, because we actually were able to extract the interesting feature of the eigenvalue. One of them was this exponential convergent method, which later on was picked up by many other people and extended in many ways, especially in the ab initio calculations. And actually, this was very useful because also use this investigation to look into the level density. As Sophia mentioned, we have this moments method. And one of the important ingredients in the moments method, which was one of the Sophia slide, was that you need to know with good precision the ground state, the energy of the ground state. The moments method is giving you the shape of the distribution, but in order to find out the density as a function of excitation energy, you need to know what to put the ground state on the absolute scale of energies. Another outcome of this investigation of quantum chaos in nuclei was related to this preponderance of 0+ state, which Calvin and his collaborator first noticed, and we added to that just the contribution of the pairing on top of end of interaction. So there we find out that actually the probability of getting 0 plus states for even nuclei increased dramatically. So this was quite useful. My title of my talk is related to actually to the weak observable. So I didn't say anything about the shell model because I knew that previous speakers will say something. I just wanted to highlight one slide. And this slide, so it's a kind of an idea how this effective interaction were derived and what was important actually for calculating anything else besides spectral level density. So in general, the having, the scattering data can be used to derive an interaction of sorts, right? And after that, you can different techniques like G-matrix or Suzuki or okay. And after that, you still need to do a little bit of core polarization. And that interaction is still not good enough, as Alfredo already told us this morning. And what Alex's technique was to do a little bit of fine tuning using only excitation energies. And include a lot of excitation energy and some range of nuclei, like SD nuclei. And you can get a better RMS here, for instance, compared with experimental data. And you can actually do a full fitting here, but it's not really extremely useful because you're not going to gain at some point from this point where USD comes out. For example, you can get an USDB, but the matrix element of your Hamiltonian will change significantly compared with what you start with. And what you start with, you know what you put in, you know the phase convention you added in. So you don't want to change too much your Hamiltonian by full fitting, so what they call is a fine tuning, just because you want to describe observables. And the observation was that you can describe observable using Bayer operators if you amend a little bit the operator by using some effective charges or effective quenching. And here is an example for the Gamow-Taylor. And the Gamow-Taylor obviously is very useful for many things, for nuclear astrophysics and also for weak interaction. Most of the beta decay and double beta decay are related to that. So at some point about 2007, we looked into the double beta decay, which clearly attracted a lot of research. And the classical double beta decay involves a process which is allowed by the standard model, namely when the 2 neutrino and 2 electrons comes out. That happened due to pairing when even nuclei cannot decay in the sampling by a beta decay because the energy of the odd is higher or not accessible. And example of that would be germanium, selenium, calcium-48. Incidentally, these are the picture created by Alex at some point. Okay, so I shamelessly use that here. And also there is a neutrino double beta decay, which is more important because we're going to prove that lepton number is not conserved, right? So here you have 0 leptons here, and you have here 2 lepton and 2 anti-lepton. The lepton number is conserved in the allowed process, but it's not here. Originally, actually, people thought that this is a more probable process to observe. That this was first estimated by Maria Goper-Meyer in the mid-1930s, and people came to the conclusion that this will never be measured because the probability is too low. That we know today that the half-life of the order of 10 to the 20 years. And this one actually has a higher probability and was most probable before 1956, 57, when parity conservation was discovered, and that changed the whole set of rules. And now people are still looking for that process, okay? So in both cases, the decay rate, which is the inverse of half-life, is proportional with some matrix elements and some phase space factor. This phase space factor is higher than the one for the two neutrino. That's why people thought that this is more probable, but because of the parity mismatching here, this additional parameter here comes out, which is diminishing significantly the process. Okay, so the goal was for us is to calculate this matrix element in a reliable way. First calculation we did was in 2007. This was calcium 48. We calculated the two neutrino matrix element, and this figure was kind of attracting many eyes because it showed how the matrix element increased with the energy of the states in the intermediate nuclei, which is scandium. This one here, this will be if it's calcium 48, this will be scandium, and this is titanium. And you can see that it's going up, and after it's going down, and essentially it's settled down to almost the same contribution like the first state. So that obviously you need to take into account the exact way the phases of the gamma of Taylor transition coming from calcium and titanium. If you take the experimental data, you don't know the phases, this is going to go up, and it's not what the experiment shows. Obviously, doing summation directly on this state is not very useful. There is a strength function method, which I describe in this paper here. I'm not going to give you too much detail right now. Many people are using this version rather than doing summation on this because this hardly, they convert not very easy. I believe it was about 500 states here to convert. So the first paper on neutrinos double beta decay is in 2010, and here we calculated again the calcium, and calcium is of course not very accessible experimentally because there's a very low abundance. But xenon is one of the most interesting one because they can create large quantities, and there's the highest lifetime limit today, which is about 210 to the power of 26 years. And we studied this in a large shell model. So we use this JJ55, which includes states from T100 up to 132. But also include after that the G9.5 and H9.5. This is a larger model space and require a little bit of treatment where the shell, the central paths need to be carefully checked out. And Alex actually came up with an interaction for this model space, which is still difficult to handle. So what we find out indeed that these matrix elements are small, and you'll see what's the implication of that. Also included some other mechanism in this paper. So all this calculation includes something called the closure approximation. Closure approximation assumes some energy in the denominator. And we are actually able to go beyond the closure approximation and do a summation on the intermediate states here in calcium. And also we did that for selenium and germanium later on. And we were able to actually show that it converged. In cases a little slower, but we were able to improve the convergence by using the actual matrix element for the closure approximation. And that gave us intermediate state in the intermediate nucleus here and how they contribute with different contribution. We found out that there is a cancellation between the spin 0 and spin 1 here. And after that, we Alex came with the idea of actually not going to the intermediate state of the gamma of Taylor, but going by two particles. Okay. 1.5, good. So recently we actually looked because in general matrix elements are spread out all over the place. The shell model are relatively low, but other model give you high matrix element. There is still a factor of about 3 discrepancies. So we try to use some statistical methods to find out which model we can select one model, we can get information from different models. So we did this for calcium 48 and xenon here, and we use 3 different effective Hamiltonian, the same model space, and we change the matrix element by about 10%. So find out that some of the observable which are here, we have 0 neutrino, we have energy of the 246 and some other observables, and so some of them are strongly correlated, some not. An important part is if you look at the diagonals here are actually, you don't see dramatic changes. It means that calculation, if you change the Hamiltonian by about 10%, you're not going to get dramatic changing like phase transition of So with that, we use this Bayesian model averaging and find out a common distribution based on all these 3 models. Turns out that one of them is significantly more important than the other, but it depends, it's very sensitive to this quenching factor for the 2 neutrino matrix element. So we came up with a common distribution, which is this red curve here, and based on that we came up with some range of the value and some matrix element. So because my time is short, I'm going to conclude by it was a great journey. Alex was extremely graceful and useful in all my time since I came here, and we did calculation and good research together, and hopefully we'll not stop here. One important observation is this robustness of this outcome of the shell model when we have small changes, which was probably not investigated enough, and we have some present and future work to do. Okay, and thank you.
Thank you very much for taking us to the weak interactions and the connection to shell model. Very brief question, comment? Minus double beta decay. So the 2 neutrino double beta decay has actually been observed, right?
Yes, yeah. Sorry, I was observing about 11 isotopes, and actually recently also the double electron capture observing xenon.
Yes. Just a question. What is the size of the model space in the xenon calculation? How big was that?
The model space in xenon, we use the JJ55, is not very large. We did about 1,000 samples here. We have some 5,000 we did not include in all the analysis, but that's one of the advantages of xenon. If I use the JJ55, it's close to the quarter of T132, and the dimension are not large because there are few holes and few parts.
Comment.
Please ask.
May I comment?
Yes, please.
In this talk, there were these right words of chaos and parity mixing, etc. And these 2 things, one can join them and get enhancement, big enhancements in the effects of parity mixing in the compound nucleus. And this was initiated in Russia and theory in Novosibirsk, Russia. And later at Los Alamos, groups of, mainly the group of Bowman David Bowman has studied it a lot. Well, I'm mentioning this because in one of my visits to MSU, we, together with Alex Brown, we actually used the shell model in high density of states to demonstrate in the shell model that this is indeed a very nice effect, which increases the sensitivity by a factor of 1,000 or so. And we published it together in Physics Letters. So there's another aspect of the work of Alex Brown. Thank you.
Thank you.
That's right, I agree. I didn't mention that, but
Shame on you. Yeah. Because the chair was stopping you.
right, I mean, you gave me 15
Yes.
minutes to do it. Right.
Okay, thank you very much. I would like to propose we only do 2 more talks and then we do the coffee break and we push the others after the coffee break. And now we are moving on to experimenters. As mentioned before, we are not only celebrating Alex Brown and the shell model, but also collaboration with the experiment. And I'm calling on Takashi Nakamura from Tokyo Tech.
Yes. Can I share the screen?
Yes, you should be able to. Excellent, we can see that.
Can you see?
Yes. Do we see the slides advancing? Because. Yes, okay. Takashi, take it away.
Okay, can I start?
Please.
Okay, thank you very much for the nice invitation. I wanted to come, but I'm sorry to say that I'm not able to come to this meeting in person. But today I'm going to talk about observation of auction 28, what's next. And before going into auction 28, I just would like to say, Alex, happy birthday. And I met Alex maybe for the first time around 95. And I stayed at Michigan State in East Lansing, September 98 to 2000, March. And I had lots of discussions on physics and other matters with Alex Brown during my stay. And when I left East Lansing in 2000, Alex gave me a nice photo book of Michigan, as shown here. And Alex was probably the only professor who gave me the farewell gift, I think. And my last visit to Michigan was in 2013. And hopefully I can see you soon, Alex. Okay. And this is the paper from my MSU days. You can see here, Alex here, and you can see also your great director, Glassmacher here, and former director of Guardian, Navin is here, and many nice people were there at that time. Okay, so today I'm going to focus on auction 28, first observation of auction 28, which was done at RIBF, RIKEN, and this was just published in Nature. And the experiment was led by Yosuke Kondo, and I actually borrowed a number of slides from him for today. Okay, so why auction 28? This can be the last doubly magic nucleus with canonical magic numbers. So we know that we have only 5 species of doubly magic stable nuclei, and we have only 7 species of the doubly magic exotic nuclei, including candidates with canonical magic numbers. Canonical magic numbers, I mean these numbers, you know. And except auction 28, the other nuclei were already observed. And some majesty established for these nuclei. But for exotic nuclei, we know that canonical magic numbers may disappear and new magic numbers appear due to the shell evolution. So the question we'd like to address here is auction 28 is it really doubly magic? And Alex actually recently published a very nice instructive paper, a review paper in here. And here he showed this plot, nuclear chart in the lower part. This is excitation energy of the first 2 plus states. So you can see red points are basically doubly magic, and he categorized this most robust pairs magic numbers for filled circles, and less robust ones open circles, and broader circles he called outposts, 4 nuclei, and one of them was auction 28. Okay, so the question I just said here is if it is within the island inversion, because it is just south of the island inversions you see here. So flow line 29 is just next to auction 28, And from the recent experiment, for instance, the gamma ray transition from the first excited to the ground state of fluorine-29 shows rather low excitation energy of the first excited state, which is compatible with a shell model like SDPFM, which showed small 0 bar omega probability. And the other experimental evidence was from about halo structure of fluorine-29, showing large contribution P3 and of fluorine-28 measurement also showed P-wave contributions, so like this. So fluorine-29 is clearly in the island inversion. The other important thing is that what is the origin of oxygen anomaly? A sudden change of drip line from oxygen 24 to fluorine-21 here. So what is known for neutron-rich oxygen isotope? We know the ground state of oxygen 25 located about 750 keV above the threshold. The width is 88 keV. And for oxygen 26, we know two states. The ground state is very unbound, 18 keV only, with respect to 2 neutron emissions, and first excited state at 1.28 MeV, like this. But nothing has been known for oxygen 27, 28, which is really difficult nuclear. Okay, so we did the environmental spectroscopy of oxygen 27, 28 using fluorine-29 beam, one proton removal reaction. So here's fluorine-29 at 230 MeV per nuclear impinged on like liquid hydrogen target, and proton is removed, knocked out. Oxygen 28 remains as a residue, but it is unbound, so it decays immediately into oxygen 24 and 4 neutrons. What we measured are five particle coincidence of momentum to reconstruct the invariant mass of the state. So in the same experiment, we also measured oxygen 27, 2 proton removal reaction of neon 29, and 1 proton 1 neutron removal reaction from fluorine-29. So this is the experiment setup we used. This is so-called RIBF summary setup. So this is a summary magnet, 2.9 Tesla. And we use fluorine-29, as I said, impinged on MINOS target. MINOS is the liquid hydrogen target surrounded by TPC to pin down the vertex point, which minimize the energy loss ambiguity. And then also we measured 4 neutrons in Neuland, as well as a standard neutron detectors nebula. And with this addition of Neuland from GSI, we could reach 50% efficiency for 1 neutron, about 1% for 4 neutron. So coming to the results, so this is decay energy spectrum, oxygen 27, 28, first 27 here. This is from fluorine-29, 1 proton, 1 neutron removal. But we actually identified the small peak as oxygen 27 events. Why? This is because after we select oxygen 26 in the intermediate state, we could see more clearly this peak. And in combination with 4 neutron measurements, we identified this first peak as actually oxygen 28, but measured with 3 neutron in coincidence. So with that, we confirmed that this is oxygen 27 ground state at 1.09 MeV. And also we could extract the upper limit of the widths as about 180 keV. So with this, we assign this spin parity of the state as 3 plus, 3½ plus, or 7½ minus. So for neutron coincidence spectrum, we could see, so this is oxygen 28 now, so we showed here 4 neutron coincidence spectrum. So you see this nice peak just above the threshold, and we extracted the energy 0.46 MeV. And the upper limit of the width is 0.7 MeV. Okay, before going into that, this actually showed that oxygen 27 decays sequentially through oxygen 26. And how about for oxygen 28? we also found that if we select, so this is oxygen 26 energies, and we saw that the experiment is in agreement with the simulation with the sequential through oxygen 26. So we identify actually oxygen 28 decays through oxygen 26 round state to oxygen 24. And oxygen 28 is actually bound with respect to oxygen 27 and oxygen 25. So yeah, this is what I said. Okay, so this is a comparison to theories. So you can see here ground state energy or mass with respect to oxygen 24, oxygen 25, oxygen 26 here, oxygen 27, and 28. Okay, so there are some variations, but we notice that actually oxygen 25, 26 are not so bad compared to theories, but oxygen 27, 28, there are some deviations for shell models, coupled cluster calculations, and the underestimation for Gamma shell model. But recently, actually, I found with this Alex paper that he actually predicted 1.5 MeV by FSC Hamiltonian shell model. And that actually, I found it is the closest prediction for this experimental value. I'm not going into detail the theories, maybe, at this point. Okay, so the question is oxygen 28 doubly magic? So what we did, what we could do was to investigate how similar the mother nucleus of fluorine 29 and the daughter nucleus of oxygen 28, because we just use one proton removal from fluorine 29. So the point is that fluorine 29 is in the island inversion from the previous experiments and also theories. So so that means that if C square S for this one proton removal is nearly 0, oxygen 28 can be doubly magic. But if it is 1, this means that the configuration between fluorine 29 and oxygen 28 is very similar. And the expanded result was a 1.36 millibarn, corresponding to C square S value of 0.48. And compared to the shell model calculation with EEDF3 interactions, which is modified version of EEDF1, EEDF1 actually predicted well this fluorine 29 reaction cross sections. And with this shell model calculation, we found C square S equals 0.68, and this shell model calculations actually show the disappearance of n equal 20 shell gap in oxygen 28, like this way. And if we assume oxygen 28 is 100% closed shell, C square should be 0.13. So this shows that actually oxygen 28 is likely to be within island inversion, and n equal 20 magicity disappears. So, but of course, about the shell closure, we of course need to investigate the separation energies, as actually Alex suggested in this paper. So he actually used this D of n as a signature of magic numbers or closure of the shell. So this is just a difference of 1 neutron separation energy of 2 neighboring nuclei. And for the calcium cases, he actually showed in his paper like this. You can see calcium 48, 52, 54 doubly magic nuclei. And just use this expression. I actually did this for oxygen isotope today. Oxygen 14, 16, 22, 24. And how about oxygen 28? Of course, we need to know now the separation energy or energy above the threshold of oxygen 29. If it is 2 MeV, it is like this, 1 MeV is like this, 0 MeV like this. So the next step for experimentalists is to attack oxygen 29 to measure oxygen 29 mass separation energy. So this is a kind of personal view about oxygen 28. So oxygen 25, 28 series provide us unique isotopic chain where 4 consecutive isotopes beyond the neutral line reveal as narrow resonances. So it provides us benchmarks for theories for the open quantum systems. And the questions I'm still having are the following. Can we understand the separation energies for these 4 isotopes? Oxygen anomaly is understood already. Is oxygen 28 spherical due to proton shell closure or egg-like structure? Proton spherical, neutron deformed. Proton shell in oxygen 28 is really closed. Where is the first 2+ state of oxygen 28 located? So this is actually the second most important study after oxygen 28 ground state observation. And how does the shell evolve beyond any 20 oxygen isotopes, oxygen 29, oxygen 30, blah, blah, blah. Okay, that's what I'd like to say. Again, I'd like to thank the collaborators, also Kondo-san for giving me the slides. And I'd like to congratulate Alex for your great achievement about shell models and great contribution to our field. Thank you very much.
Very much, and we have to congratulate you to your beautiful experimental results, which are really a milestone. Any quick question, Don?
On that phase-based calculation you showed, did that include the NN final state interactions? Or was it just pure
Which one? You're talking about this this one?
There, yeah. You said 5-body phase space.
Yes, yes. So this is 5. So what was the question? This is 5-body phase space, actually.
Yeah, is it just pure phase space, or does it also include the NN final state interactions?
I think this is just a 5-body phase space.
Right. So I would really expect that to be significantly modified by the NN final state interactions.
Okay, but anyway, what I'd like to emphasize here is if we select, so E012 means that if we have 4 neutrons, we just add up the first lowest 3 particle energies like this. So the lowest 2 neutron energy is actually peaked at oxygen 26 ground state. So this is a strong indication anyway that it decays through oxygen 26. But maybe, yeah, I agree. Maybe if we include final state interaction, maybe the spectrum may be changed. Thank you. Thank you.
Thank you. Okay, time to move on.
Thank you very much.
Takashi. Speaker before we take the coffee break earlier is Andrew Stutchbury from Australian National University, and he will take us to moments. Scanning for viruses. Tell us you did not bring any viruses from Australia. Please. Okay, can we check that it advances also on Zoom?
Hello?
Can you just advance the slide?
Oh,
because it
with
got
this,
stuck.
okay.
Seems to be sharing the wrong.
It's not. It's not.
Doesn't seem to be event. It's not showing the right screen.
So I stop share and we try this again.
need to change the order of those operations. You might need to share it and then, do the slideshow and then share.
I cannot do the slideshow and then get back to Zoom, so.
Full screen, full screen, please.
Write that down.
Okay, so we try to see it on. Okay, that's a new feature.
Well, again, it's my real pleasure to be here and wish you a happy birthday, Alex, and talk a little bit about some of the physics that we did on one occasion. I'll pick out one occasion of the many we visited the Australian National University. I think I'm probably the only person here from the Southern Hemisphere, so the second experimentalist. I'm going to talk mostly about E0 transitions. I'll say a little bit about shape coexistence and E0 transitions and then relate that to G factors in calcium and argon isotopes and then make some conclusions looking to the future. So first thing I'll start talking about is a model that Alex developed for electric monopole transitions when he was visiting Australia. I guess it was 2016. It happened to be that Adam Garnsworthy from Triumph was visiting at the time, and Tibor Kabetti and I had been working on developing a pair spectrometer, initially to look at the Hoyle state, and we measured the radiative decay of the Hoyle state. Paco referred to calculations on that earlier. While Alex was there, he developed this new microscopic method for dealing with E0 transitions, monopole transitions. So the monopole operator is quite simple. It's just measuring the radial distribution of charge in the nucleus. And the consequence is that to get an E0 transition, the initial and final states must have a different mean squared radius. They must have a different shape. And the two states have to be mixed. So often this is treated in a two-state model. This is the E0 strength. These are the mixing amplitudes for the two states, and then you have the difference in the mean squared radii and the nucleus. So that's a kind of empirical two-state mixing approach that's often used. Well, the objective was to go more microscopic, but before I talk about the theory, let me show you the apparatus. This is the Super E at ANU. It has been used for many years for conversion electron spectroscopy, but Tibor and I got some money to upgrade it to make it into a pair spectrometer. The main component was to replace a single silicon FET with an array of 6 SILI detectors. And the idea is that down the bore of the solenoid, which is here in reality and here in this computer rendered diagram, the electrons and positrons come out of the target and spiral with opposite helicities down the bore of the solenoid, magnetic field in this direction. And we have these baffles in place that prevent the detectors from seeing gamma rays coming from the target. So you detect an E0 transition by adding together the electron and positron energy, and you should get a peak at the transition energy twice the electron rest mass. And the first time we saw that was late on a Friday night when all the grad students had gone home, and Tibor did a dance around the control room. I wish I had on video, but anyway. I mentioned the initial emphasis was on the Hoyle state, but today I'm going to focus more on calcium-40 and nuclei in the FP shell. So we know that shape coexistence is important in these nuclei and that there are multi-particle, multiple excitations in calcium-40 and also nucleus. This is just another slide of the solenoid, but showing the resolution you get with this magnetic separation in a silicon detector compared with previous work that used E delta E with scintillator detectors. So back to the paper and Alex's model. Well, in a kind of simplified experimentalist way of describing things, we start off with a shell model and orbital occupancies of the nucleus of interest. So those orbital occupancies are then allowed to influence the self-consistent potential in an energy density functional model. That, of course, means that you'll get different radial wave functions, which will give rise to E0 transitions. So that's a very simplified statement of the procedure. Forgive me for putting up this table. We'll just focus on the key points. There's a selection of nuclei here. We're looking at 0 to 0 transitions where the transition strength, or in this case, the matrix element extracted from it, is known. The order here is really in terms of the theoretical sophistication rather than mass number or anything like that. And over here is comparison between theory and experiment as a ratio of theory to experiment, and there's 3 columns. This first column is kind of a benchmark, which is the energy density functional valence calculation. And if you just glance at that, you can see that the agreement with experiment is not great. The difference between theory and experiment can be an order of magnitude in either direction. On the other hand, if we go to Alex's model, it generally gets within a factor of 2 of experiment. The 2 columns here are 2 different Skirm interactions, which you could say is giving an estimate of the theoretical uncertainty, but it's also telling us that the calculation is sensitive to some of the Skirm parameters. So this is a significant improvement. Now, I'm going to show you now a comment that Alex made in the paper that's almost prophetic, and probably you've forgotten, Alex, that you wrote this. There was one particular case, E0 matrix element for the second excited, or the first excited, but second 0 plus state, 58. It's much larger than the experimental value. There was also an issue with the E2 matrix element. And the comment was made that the minimal resolution of both of these problems requires a remixing of the theoretical second and third excited states. So in effect, you go from what's effectively a 2-state mixing to a 3-state. So that brings me to this recent work, which was published last year in PRL. Measurements were done at ANU with the Super E, looking at the E0 transitions in calcium-40. So in calcium-40, we have a essentially spherical ground state. The first excited state has a rotational band built on it, and it's normally deformed. And then the second excited state also has a rotational band built on it, and it's super deformed. And what we found in this work is that there's destructive interference. There's this decay was observed from the super deformed band through the ground state, but it was weaker than you would naively have expected given the shape difference between these 2 configuration states. And here's a cartoon here done for publicity purposes, trying to explain these different shapes and the fact that the outcome depends on interference between those components in the E0 strength. Now, our collaborators, Japanese theoretical colleagues, have calculated calcium-40 states and related states in sulfur-36 and argon-38. And there's a calcium-42 number there as well, I think. They get a pretty good agreement between theory and experiment. So let's unpack that calculation. So these are large-scale shell model calculations, allowing up to 10 particle, 10 hole contributions to the wave functions. And perhaps not surprisingly, the ground state is mostly 0 particle, 0 hole with a little bit of 2 particle, 2 hole. The first excited 0 plus is mostly 4 particle, 4 hole. This is normally deformed state. And the super deformed state is mostly 8 particle, 8 hole. This picture up here is it's intended to give an indication of why we get the destructive interference. So the bottom panel is showing the matrix element, the cumulative matrix element, as you sum up the contributions from the different numbers of particle hole excitations. And the upper panel, which is referred to as the overlap in the paper, is more or less a contribution to this matrix element. We sum these with a phase factor to get these. And the difference between the third, the super deformed, the ground state transition, and these other two is that this matrix element changes sign only once for these two transitions, but twice for this. And that leads to the small E0 strength between the super deformed band and the ground state and super deformed band here. So these structures are identified throughout the calcium isotopes, and we know the states are multi-particle, multi-pole from transfer reactions, and we see rotational level spacings. If we look at calcium-42, on the right here are transfer reaction data on left B2. I don't want you to look in any great detail at this. It's safe to notice that it exists. But if you look at the transfer reactions, you can see that this population of the ground state 0 plus and the first excited 0 plus, and you see 2 2 plus states and 2 2 plus states. And you can look at this transfer data and therefore infer mixing amplitudes between these different configurations, the ground state, spherical, and the excited deformed. And if you take those mixing amplitudes and put it into a two-state mixing, you get this. Now, I don't expect you to take in all these numbers, but the gist of it is that the two-state mixing between the shell model states, so essentially a pair of F7 neutrons, and the deformed band agree within about plus or minus 10%. Which brings me to the G factors. So for a long time, we've known that the G factor of the first 6 plus state in calcium-42 is fairly close to the Schmidt value. It's fairly close to the shell model calculations. It's mainly an F7 neutron pair. On the other hand, the first 2 plus state has a slightly positive, but consistent with 0 G factor. And this mixing in this between the deformed and the shell model is about 50-50. And if you add together a 50% G factor of about plus 0.4 from a collective structure with the spherical shell model value, you end up with about 0. So that nicely explains that. We see that in calcium-44, the G factor actually goes more positive. So you might say there's more deformed admixture. I think it's probably more likely that the admixture has a higher proton component. It's supposedly a proton 2-hole proton excitation. And then when we come to calcium 46, we're getting close to calcium 48. The glib statement is that calcium 48 is a better shell model core. Perhaps more accurate thing to say is that the deformed states in calcium 48 are at higher excitation energy and in fact haven't yet been identified. So back to Alex and shell model and G-factor measurements. These two papers on the first experiment I did here many years ago now at NSCL, we proved we could measure G-factors with reasonably good precision. In fact, these measurements were as good as stable measurements. Sulfur 38 and sulfur 40. Alex did the theory for these. And we got pretty good agreement between theory and experiment. Now, fortunately, in this cases, the shape coexistence isn't really coming into play. But when we go to the argon isotopes, and these also were measured here, and to my embarrassment have not yet been published, if we compare the calcium isotopes and the argon isotones, we see exactly the same pattern in the G factor. Argon 40 and calcium 42, the G factor is about 0. Calcium 44 and argon 42 is greater than 0, and 46 and 44 is less than 0. So my conclusion is that the G factors in the calcium and argon isotopes, neutron-rich argon isotopes near calcium 40, are sensitive to shape coexistence and shape mixing. And the next steps, experimentally, there are moves afoot to do more extensive calculations of measurements of Coolx in the stable calcium isotopes. But what would be really nice is a microscopic theory for the multi-particle, multipole excitations, like what was done in calcium 40. These measurements were done back around about the time that Alex was visiting in the nickel isotopes. So this is Lee Evans, a student of Alan Garnsworthy. And you see strong E zeros here, which get weaker as you go further from nickel 56. So I'm suspecting that these zeros, which are bigger than Alex's model, are also influenced by shape coexistence in the nickel 56. Now, just to change gears again slightly, but tie back into one of the themes that's been talked about a couple of times this morning, and that is developing effective interactions for the shell model spaces. This is usually done by fitting energies, and then you check against the moments and other observables. And in the moments data, it's usually the ground states that have the biggest influence on at least what you look at. I've discovered a couple of cases where if you look at excited states that are fairly close, the shell model gets the character of the states inverted according to the G-factor measurement. So here's one example in iron 55. These two 7/2 states have opposite characters in theory and experiment, but they're close in energy, so maybe it doesn't matter. And then going to high spins, this is JJ44b in strontium 84. These pair of 8+ states and pair of 10+ states also both have their character inverted. So one's dominated by the G9 proton and the other by the G9 neutron. And the interaction's getting those in the opposite order to what they are. So let me wind up. Shape coexistence and shape mixing appear to be present through the F7/2 and FP shell. And it's likely in neutron-rich as well as the stable isotopes. We need large basis shell model calculations that can handle the presence of the multi-particle, multipole deformed states. We deal with these things. The E0 transitions, we have a good theory that Alex has provided for the 0 to 0, but we're finding that the J to J transitions are more of a challenge, and that's also the case experimentally. I've observed that the G factors can be sensitive to shape mixing, and then I just pointed out these couple of cases where the G factors are indicating that the fitted interactions haven't quite got right some of the two-body interactions. But on the other hand, the states are close together, and so maybe it's not the end of the world. And so with that, I'll conclude. Thank you.
Thank you very much for this nice talk, and maybe it's not the end of the world, but almost the end of the session. Questions for Andrew? You really want those croissants outside, I know, me too. Okay, I think you're free to go.
Okay, thank you.
And then after the coffee break, we will have 2 more experimental talks and then the discussion panel. And the session will be shared by another co-organizer, by Robert Janssens from UNC.